Who are the laureates of the Nobel Prize in Physics this year? What did they do? And why does their work matter? Hi everyone, it's Elisa here. In this video, I'm gonna give you detailed answers to all these questions. The first thing, who are the winners? The Nobel Prize in Physics in 2025 was awarded jointly to Joan Clark, Michel H. Devoret, and Joan M. Martinez. All of them were from the same research group at the University of California, Berkeley. When they did this groundbreaking work 40 years ago, their roles were like mentor, postdoc, and PhD student. A second thing, what did they discover? According to the Nobel official website, the prize was awarded to them for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. So here comes the first problem. What is quantum mechanical tunneling? Our everyday world follows the rules of classical physics. If you throw a tennis ball at a wall, it will certainly bounce back. That's just how our macroscopic world works. But a microscopic world is described by a totally different set of rules, called quantum physics. A tiny particle can sometimes just go through the barrier and appear on the other side. It's super counterintuitive, isn't it? This is the so-called quantum mechanical tunneling. This phenomenon was discovered soon after Erwin Schrödinger published his famous wave equation in 1926. As it usually happens in very small dimensions, like electrons and atoms, this kind of scale used to be too tiny to observe. And what is amazing about the three laureates' work is that they have made the walking through wall tricks visible on macro scale. We can see it with our own eyes. And before telling you the details about their experiment, there are something we have to figure out first. In a normal conductor like metal, electrons are fermions. And when a current flows in, the electrons will be easily distracted. Such chaos will cause resistance, and voltage appears. But when a material becomes a superconductor, something magical happens. Electrons pair up to form Cooper pairs. Then it will be much harder to distract them. They move in a synchronized way, flowing without creating resistance and voltage. This is the so-called supercurrent. And here is the coolest part. Let's see the setup created by the scientists. They built an electric circuit made from two superconductors, separated by a thin layer of non-conducting material, creating what's called a Josephson junction. Inside, all these Cooper pairs lost their individuality, which means they acted together as one single quantum entity. You can imagine a single big particle filling the whole circuit. According to the original Josephson junction theory, if you push a current through this junction, there will be two possibilities happening to this circuit: a zero voltage state and a state with a measurable voltage. In their experiment, they used a Josephson junction with billions of Cooper pairs. It's truly a macroscopic object. And they have proved that the circuit could switch between the two states. Furthermore, the researchers showed that the system is quantized, which means atoms absorb and emit energies in packages called quanta. This is an essential property of the quantum world. So finally, they managed to demonstrate two quantum properties: quantum tunneling and energy quantization in a macroscopic system. Question 3. Why is this a big deal? Clark and his team's research has brought the rules of quantum physics from a subatomic world onto an electric chip, from microscopic to macroscopic. This was a huge breakthrough in our scale of observation. What it means is that now we can observe and study quantum activities in a much more accessible way. This paved the way for technologies like building quantum bits for quantum computers. And the most typical benefit is that you can couple these superconducting atoms to mechanical oscillators and then probe properties of the mechanical oscillators. This is precisely the important platform for developing quantum computers. So there you have it. What is Nobel Prize in Physics this year all about? Why is it so brilliant? And what's its real-world value? Does it all make sense right now? Thanks for listening!